Everyone is very concerned about what's going on in the oceans. In 2023 and 2024, temperatures weren't just higher than normal, they were much higher than normal. Everyone's very concerned that maybe there's more heat energy stored in the oceans than we thought. Maybe we're in more trouble with climate change than we thought. So in this video we're going to look at how climate change is affecting the oceans and the impacts that the oceans is having on the rest of the Earth. There are several theories about why the oceans were so hot in 2023 and 2024. There was a volcano that erupted, and that put a lot of water vapour into the atmosphere. As we see later on, water vapour contains a lot of heat energy. Also, there were fewer clouds in the last couple of years. Why were there fewer clouds? Nobody knows. The thing about the oceans is they have absorbed a lot of heat. They have absorbed 93% of all the excess heat energy caused by climate change, although they do account for 71% of Earth's surface, and they are on average 3,600 metres deep, so there's a lot of ocean there to absorb the heat. Also, the oceans have what scientists call a high heat capacity. That means to increase the temperature of water, you have to apply 4 times as much energy as you would if you wanted to increase the temperature of something on land by the same amount. So like tarmac or soil or something like that, it takes 4 times as much energy to heat the water up, which is good because the water can absorb 4 times as much energy by only heating up the same amount, which helps to reduce the impacts of climate change. The scientists think they do have a good understanding of how much heat the oceans have absorbed. There's the National Oceanographic and Atmospheric Agency. It's an American agency. It's called NOAA. That has a program called Argo, and that runs thousands of automatic buoys, or buoys as they're called in America, thousands of automatic buoys. They're all over the oceans, and they automatically dive down to different depths. They record the temperature and salt concentrations, and so as far as we can tell, the oceans have absorbed as much heat as we thought, and that isn't the reason why they're suddenly seen to be much hotter than normal. The number one thing though that affects the temperature of the surface water isn't the sun or the atmosphere heating it up. It's mostly affected by how much cold water from the depths is mixing with the surface water. So the first couple of centimetres of the surface water is heated by the sun. The wind blows on the surface of the ocean, it causes waves, it causes mixing of the water, and for about 100 metres it gets the full benefit of that warmth coming through from the surface, from the sun and from the warm atmosphere warming up the water. Then when you get down to about 700 metres, in the tropics, in the part of the oceans that gets the most heat from the sun, there's something called the thermocline, and it's a boundary between the hot water on the surface and the cold water in the depths. It's called a thermocline, and you can see it in this diagram how much of a difference it makes. In the polar regions there's no thermocline because the water is cold all the way to the top, and in the between the polar regions and the tropics, in the temperate zone, sometimes there's a thermocline in the summer. In the winter time there's not one, but that thermocline is causing the water on the top to become more stratified, that the water on the surface is becoming warmer, it's expanded, it's lighter, it's less dense, so it doesn't mix as well with the deeper parts of the ocean as it used to. And I can't help wondering if this is the number one reason why the ocean surface temperatures were so high in 2023 and 2024, especially because they were El Nino years, and in an El Nino the trade winds in the Pacific reduce. They don't blow so much on the Pacific. There's less mixing of the water. It's accepted that the surface waters are always warmer in El Nino years because there's less mixing of the water and because there's less wind. Climate change is causing the oceans to become more stratified, and that's causing problems, for example, with how much CO2 is being absorbed. Each year the oceans absorb 3 billion tonnes of CO2. That's nearly as much as the forests absorb. The CO2 in the atmosphere mixing with the oceans, with waves. The CO2 dissolves. It's processed by phytoplankton, and phytoplankton are like algae, they're tiny little creatures, and they absorb the CO2 through photosynthesis. They mix together the CO2 and the water in the ocean, and they use it to produce carbohydrate that they use to build their bodies, and they produce oxygen, and this is all powered by sunlight. And half of all the oxygen in the atmosphere is produced by phytoplankton. Phytoplankton can't swim, so they rely on the oceans overturning to keep lifting them back up to the surface where they can photosynthesize. There are all sorts of problems that might affect phytoplankton. First of all, because the oceans are becoming stratified, there'll be fewer nutrients coming up from the depths. They rely on things like iron coming up from the depths. Global scale computer models tend to agree that there will be a decline in phytoplankton in low and mid latitudes as the water warms and the surface layers become insulated from the supply of nutrients from below. In the North Atlantic, for example, plankton have already declined over the last 50 years. However, what happens further up the food web, up to the stocks of commercially exploited fish, is far from clear. Some models suggest little change in fish, and others project a major decline. Some findings reveal that when climate warming reduces phytoplankton levels by just 16 to 26%, as projected by global models in regions like the North Atlantic, the carrying capacity for fish plummets by 38 to 55%. Another problem is there's so much CO2 in the atmosphere, so much CO2 mixing with the ocean surface, that the oceans are becoming slightly acidic through the production of carbonic acid. CO2 and the seawater react with each other. That means there's less carbon available for the phytoplankton, less carbon available for fish who want to use it to make their bones, less carbon available for fish that want to build their shells. It's thought that if we carry on as we are, by 2100, the oceans will be so acidic it will start to dissolve the shells of some shellfish. Also, because the oceans are becoming more stratified, they're becoming saturated with CO2. They can't absorb, or some parts of the ocean are no longer able to absorb so much CO2. And in fact, in some cases, they actually, instead of absorbing it, they emit it back into the atmosphere. In some places like the Atlantic, where there's the Atlantic meridional overturning circulation, when that water dives down at the Labrador Sea or the Norwegian Sea, that water goes down, it takes all the carbon that is absorbed from the surface and it locks it into the oceans for 1,000 years. As the oceans become stratified, there'll be less mixing going on. So that's the boring old CO2. Now, something much more interesting, the impacts that the oceans are having on Earth's warming. And we're going to follow the science through, and it's very simple science, I think you will have learned at school. But I think by using that simple science, you'll be able to see something that scientists only realised for the first time in 2018. So pay attention, and every time I say the word evaporation, wake up and take notes, okay? So we're going to go through how the oceans affect Earth's energy balance and how they affect land as well. And I could do that by showing you these diagrams. There's a constant 342 watts of heat energy arriving in the form of short wavelength infrared energy, 342 watts per square metre of Earth's surface arriving all the time from the sun, day and night, but 30% of that never gets as far as Earth's surface. It's either reflected straight back into space by the clouds, or it's scattered into space by the atmosphere. The remaining 70% of sun's heat energy that's arriving on Earth is 239 watts per square metre. Of that, 65 watts per square metre is absorbed by clouds and aerosols. So it's in the atmosphere now. It's been absorbed by the clouds and the aerosols, which leaves 174 watts per square metre of the Earth's surface, makes it actually to the surface. And of that, 24 watts per square metre is lost in convection or conduction. So convection is where heat is taken away by air currents rising off the surface of the Earth, and conduction is where heat is lost from the surface of the Earth just by the atmosphere touching it. The air conducts the heat away. And 78 watts per square metre is lost through evaporation. So out of that, only 72 watts per metre square directly warms the surface. So that's the heat energy coming from the sun, arriving at planet Earth, being absorbed by the atmosphere and being absorbed by the surface, heating up the surface of planet Earth. Planet Earth also emits its own infrared energy because it's warm. All warm objects emit heat themselves, they all give off heat, and they give it off in the form of infrared heat. The hotter an object is, the shorter the wavelength, so the sun's heat arrives as short wave infrared heat, and that's why it's able to go through the greenhouse gases. Short wave infrared heat can go through the greenhouse gases. Cooler objects like planet Earth, they emit infrared light, but they emit it with a longer wavelength, and that longer wavelength means some of it will go through greenhouse gases, but some of it will also be trapped, and this is why we're warming up. So there's a constant 239 watts per square metre arriving at planet Earth's surface, and there's 230 watts being constantly emitted by planet Earth back into space, which is why we have climate change, because every square metre on planet Earth is receiving on average an extra 9 watts of heat energy. That's causing us to warm. Sooner or later, planet Earth's surface will warm up so much that it will increase the amount of infrared heat that planet Earth is emitting, and eventually it will overcome the greenhouse gases and Earth's energy balance will be restored. The oceans have always been cooler than the scientists thought they should be, and they thought that was because, well, seawater has a much higher heat capacity, so it will be absorbing 4 times as much heat for the same temperature increase. The contrast between land and ocean temperature change will strongly shape the global pattern of future warming and has important implications for humans. We are, after all, a species that much prefers to live on land. But what drives this warming contrast is a deceptively simple question, but one with a much misunderstood answer. Simple physics suggests that when you put more heat into the climate system, land should warm more quickly than oceans. This is because land has a smaller heat capacity than water, which means it needs less heat to raise its temperature. But when they looked into it, they said, well, one day we should get to a zero carbon economy. Concentrations of CO2 will stabilise in the atmosphere. The amount of heating will stabilise, will be a hotter world to live in, but it will still be stable temperatures. And they thought at that time the seawater and the atmosphere and the land would all get to be the same temperature, because just as though you left a glass of ice water and a cup of hot coffee in a room for hours or days, in the end the ice water, the coffee and the room would all have the same temperature. The temperature would just spread out and even out. They thought, well, that would happen to the oceans, but when they looked into it, when they ran the computer models, they realised the oceans will always be cooler than they thought they were. As it happens, the average surface temperature of the oceans is 21 degrees Celsius, and they measure that between 60 degrees latitude north, which is just above Britain, and 60 degrees latitude south, which is just below South America. Average sea surface temperature, 21 degrees Celsius. Average land temperature, 15 degrees Celsius. But they're still cooler. The oceans are still cooler than what the scientists thought it should be. So when they looked into it, they said, why is it that when everything's stabilised, when all their temperatures should be averaging out and equal, why is it the oceans are still losing heat? And if we look back at this diagram, which shows how the energy is spread around the Earth, 72 watts goes into heating Earth's surface, but 78 watts per square metre is lost in evaporation. It's an awful lot of energy. There's only 174 watts per square metre arriving, and of that 78, so what's that? That's 100. Is nearly half of all the energy that arrives on planet Earth goes into the atmosphere in the form of evaporation. Oceans are responsible for 90% of all the evaporation, and of that remaining 10%, most of the evaporation, it comes from trees. Oceans, which have unlimited water to evaporate, can efficiently cool themselves in a warming climate by evaporating more and more water with only a small temperature increase. Continents, on the other hand, typically have limited moisture available, and so evaporation is constrained. So evaporation, let's look into that. This is an important part of us solving the clue that scientists only realised in 2018. So we've done heat capacity of water. Now we're going to do phase change and latent heat, which I think you should remember from school. When water evaporates, it takes heat to change from a liquid into a gas. To increase 1 cubic centimetre of water by 1 degree Celsius takes 1 calorie, and it's a calorie spelled with a small c. If you're on a diet and you're counting calories with a big C, which is 1,000 times more. So 1 small c calorie will heat 1 cubic centimetre of water by 1 degree Celsius. and 0 degrees Celsius water freezes into ice. 100 degrees Celsius is the boiling point for water. So you need 100 calories, small c calories, to go from 0 to 100. To turn 1 cubic centimetre of water that's already at 100 degrees Celsius, but it's still water, into water vapour at 100 degrees Celsius. So it wouldn't be an increase in temperature, you'd just be what's called a phase change, from changing it from a liquid into a gas. Would take 540 calories, small c calories. It's an awful lot of energy, and that locks the energy away. So when the oceans experience evaporation, as the water surface is so hot now, it's warmer, so it's experiencing more evaporation, that evaporation is locking away 540 calories of heat energy for every cubic centimetre of ocean that evaporates. This is why this number is so high compared to all the heat that's arriving on planet Earth's surface. And you know that, don't you? When you sweat, you have the sweat on your skin evaporates, that cools you down. The same thing is happening to the oceans. Even when temperatures stabilise and CO2 concentrations stabilise, the oceans will carry on losing this heat because it's evaporation. The water vapour, which is produced, rises up because it's warm and light, and it rises up into the atmosphere, and it spreads itself over a wide area. Eventually, though, it will reach such a high altitude, it will be so cold that the water condenses, and just as when the evaporation took place, it absorbed heat energy, 540 calories for every cubic centimetre of water that evaporated. When it condenses into rain, for every 1 cubic centimetre of rain, it releases into the atmosphere 540 calories. It's a lot of heat, and everyone in the world experiences that heat, but only some people get to receive the rain. And what parts of the world get to receive the rain depends on something called Hadley cells. I'll show you that. If you have a look at, for example, Africa, you can see where the equator goes through Africa is beautifully green and verdant because that part gets a lot of rain. North Africa and South Africa, there are deserts, because that's just the way Earth's atmosphere works. Some parts lose water through evaporation, some parts gain water through rain. And you can see here, this Hadley cell just carries on, doesn't it, through into China, into America, South America as well. So now we're in a position to sum up the facts we've discovered during this video and see if we can solve the mystery that scientists only worked out in 2018. So far we know the oceans lose a lot of water and a lot of heat through evaporation. That water vapour goes high up into the atmosphere. It spreads the heat out all the way around the world. Only some countries get the rain. And trees are also responsible for a lot of evaporation. Not as much as the oceans, but there's still a significant amount of evaporation coming from trees. Can you see what the problem is? If you live in a part of the world that receives water, if you're one of these green areas, then you'll receive water, you'll have trees if you haven't cut them all down. Those trees, through the evaporation, a significant amount of evaporation, will help to keep you cool. If you live in one of these desert areas, or areas where there are fewer trees, it's because you're not receiving so much rain. And even if you were, there wouldn't be any trees to cool you using evaporation. So the thing that scientists discovered in 2018 for the first time was, no matter where you live, at what latitude, how much heat you have, if you don't have rain, you won't have trees, you will suffer climate change much worse, because your temperatures will be higher at ground level because of a lack of evaporation. This insight allowed us to derive an equation for the land temperature change, which we published in 2018. What our equation shows is that the response of land temperature to climate change depends on two factors: ocean warming and how dry the land is in today's climate. The drier the land is, the more it warms. The theory has been verified by climate models using observational data over the past 40 years. The theory explains why land warming is expected to be particularly severe in dry, arid, subtropical regions. The other thing to keep in mind, if you live in a country like Britain, which is an island, and it rains a lot, all the water comes off the Atlantic. If you live in Britain, which is an island, then you're surrounded by oceans or by the sea that's constantly evaporating. Even in cold weather, there'll still be some evaporation. Then that ocean is helping to keep you cool. And that's, if you live in a coastal area or somewhere where you get the benefit of this cooling, then you're said to have a maritime climate. If you live in a big landmass like Russia or North America, you're said to have instead a continental climate. And you'll know if you have a continental climate because it's very cold in the winter and very hot in the summer, because Earth has only 1/4 the heat capacity of the oceans. So if you're surrounded by the oceans, if you have a maritime climate, then in the winter time the oceans will release heat energy. They're full of heat energy, 4 times as much than the land. In the summertime they will absorb more heat energy because they absorb 4 times as much heat energy for the same increase in temperature. Plus there's the evaporation. If you live in, say, North America, in an area with few trees, you'll know you're in a continental area because it'll be cold in the winter time and hot in the summer, because you won't get the same smoothing effect from the oceans. And you live in a part that doesn't have many trees because you don't get a lot of rain. Then whatever temperature increase we think we're going to get, you'll have more of a hard time of it because there'll be no trees there and no evaporation to help to keep you cool. Looking at Australia, I can't decide whether it has a continental climate or a maritime one. Obviously it's a massive amount of land, it's very arid. So in the centre of Australia I can see that will have continental climate. But I think most Australians live along the coast, so maybe they'll still benefit from the cooling effect of the oceans. So what did we have? We had carbon dioxide absorption by the oceans, everyone knows about that. We had Earth's energy balance and how the oceans affect that. I think that's fairly well known. The one thing is new though, fairly new, to science at least, is this effect of evaporation from the oceans. That the oceans do have a good effect of absorbing heat energy and helping us. When we get to a zero carbon economy, temperatures start to fall, the oceans will carry on the warming a bit longer because they've got all this heat absorbed, and they'll take them longer than the land to emit it. But we think that's okay because we think the scientists have a good understanding of how much heat is in the oceans, so that shouldn't affect Earth's equilibrium climate sensitivity, which is the subject of another video and is still a subject of debate for the scientists. But we think that shouldn't be affected by the water. But the oceans, although they do absorb a lot of heat, they do emit a lot of heat to the land as well. So it's good and bad. That's the end of the video. Thank you for watching. I can't think of any news updates this time, so I'll see you next time.